All right, folks, we're going to get started. Welcome, everyone, to the first robotics seminar of the 2024-2025 season. It's a pleasure to have you all here, and I hope that this will be a strong kickoff to the year. We have a wonderful speaker to open the season with, but before I tell you about her, I want to give a quick reminder to those of you who are juniors or seniors in or interested in the robotics minor. As you probably know by now, there is a new requirement for the minor, and that is attending 5 robotics seminars during your junior and senior years. So if you are a junior or a senior and this is something that you want to participate in, please sign up. We have a sign-up sheet next to that exit over there. And so if you've signed up already, great. If you haven't, you can sign up right now. I see that someone's already grabbing the sheet and they'll pass it around. If not, just sign up at the end. Just don't forget to do so before you leave. All right, so with that out of the way, it is my pleasure to introduce you to Daniela Mitterberger, who is a faculty member at Princeton University. She joined in January of this year, 2024, as an assistant professor in architecture. And her work, which she will be telling us about, is really at the intersection of architecture, robotics, and human-centered technology. And in particular, she's been thinking a lot about ways to use extended reality and digital fabrication tools to augment people and assist them in manufacturing and in particular in construction processes. So this is really exciting. And it's very much an up-and-coming area of research that Daniela has been very much leading for the past few years. Before coming to Princeton, she was at ETH in Zurich, in Switzerland, where she got her PhD, and she was there as a postdoc after her PhD, which she got in 2023. And she is also the co-founder and director of MADE, which is, it's got a name in German that I will not butcher in front of you all, but you can look it up. It's a new architectural practice that's based in Austria. You know, in addition to multiple awards that have recognized her work in the past few years, because the work is very exciting and also artistically relevant, she has been at multiple exhibitions all over the place. I don't know them by heart, but let me just read you a couple of them. So the work has been exhibited at galleries, institutions, and events, including the Venice Biennale of 2021, the Princess of Austria Awards 2021, the Seoul Biennale of 2020, Ars Electronica Linz in Austria, MAC Vienna, Melbourne Triennial, and the Academy of Fine Arts in Vienna, and HCA grads. So as you can see, you know, it's really our privilege to have Daniela at Princeton, and in particular, very exciting to have her opening up the 2024-2025 robotics seminar season. So with this, thank you very much, Daniela, for being here, and I'll pass it on to you.
Thank you very much. I hope you can hear me well. Perfect. I managed to turn it on myself. Thank you so much for the invitation. It's very exciting coming up to your labs here, and I always like to cross over disciplines. I think that's a really great opportunity. Please don't hesitate to ask me also questions during the talk. Otherwise, we get the questions at the end. If anything is unclear, just raise your hand and ask me. So Again, my name is Daniela Mitterberger, here new professor at architecture, co-founder of MATE. And if you want to write me or contact me after the talk, or if you have more questions or more interested in any of the things, please let me know. Write me an email. Don't be shy. For the people that have never seen the architecture lab, here you can see it. It's directly behind Frick Chemistry Building. It's our robotics lab. And I started to work there. It's called Embodied Computation Lab. And they mostly hired me to actually start to include more human interaction and human in the loop in digital construction and robotics. So since a few months we found the name of the lab, so it's an extended augmentation lab in architecture, and our aim is to explore technology as a primary mediator for structuring our relationship with the built and the natural environment. Here in the background you can see one of the works that I'm doing actually with my practice in Innsbruck in Austria, where we mostly focus on large-scale garden installation with robotics. I will not show work of that one this time. There we explore a lot of the research that we do in academia in a more artistic context and a more broader context without the strict boundaries of academia, I always say. This is my team. Two of my PhD students are here today. I also supervise and co-supervise and have collaborators still in Europe at ETH Zurich and TU Munich that we continue work with also on a more global scale. Good, let's get it started. So what is my work about? So my research includes domains such as human-machine collaboration, construction robotics, interactive fabrication, adaptive computation, and extended reality systems. Why is that important in architecture? So in architecture we say that we have digital and robotic fabrication around 12 years now. And it brought us a lot of great things, right? It brought us that we can build more custom, complex, customized, precise structures. Compared to manual fabrication, machines are very good at repetitive tasks. So machines are very good at lifting heavy loads. They can provide high precision, as you all know, as you work with robots. But if we look especially at construction robotic or large-scale robotics, you will see that most robotic construction processes are feed-forward and aim for full automation. So for the last 12 years in architecture, everyone aimed for full automation. But of course, full automation in architecture are based on well-defined linear sequences of actions. So where the work environment, the materials, and processes have to stay constant. So this, of course, brings a lot of limitations with it. This slide shows these limitations. So full automation almost requires something like this, especially when we talk about large-scale robots that are not made to work in close proximity with humans. And if we take a look at what happens in architecture, we see we break these rules quite constantly. And the reason for that is that if we look at what we use robotics for in architecture, is that a lot of the processes that we work with are unpredictable, they're inaccurate, they're complex, and they involve materials with nonlinear behavior, such as, for instance, as you can see here, mortar. And it's especially these characteristics that make these processes very difficult to automate, and why most of them still rely a lot on manual labor. So we humans are very good to react quickly and improvise to complex situations. Due to that, we have a thing called tacit knowledge, we have context awareness, we are dexterous, and we are very good in working with something like mortar. And this is also the reason that when we see robotics in architecture, we always still see a human in the picture. For a long time, these pictures were not shown at conferences or things like this, because it was seen as something that is weakening the project. Actually, humans were and are still very necessary to assist the shortcomings of robotic fabrication in architecture, which is, in my opinion, a good thing, because it's okay to say that we humans can do something that robots cannot do. The real problem comes when we see that the human actions, like for instance welding the joints, is not included into the digital control logic. So that means human interaction, and we have a lot of them if we look at all the possible interaction that is out there, is not instructed and not included, cannot be controlled, and cannot be told to other people if a task was finished or how a task should be done. So now the question is, if for the last 12 years we do robotics, how come that no one actually started to research on this? And it's really a research field that started when I started at ETH Zurich 4 or 5 years ago. And there are three main reasons. The first main reason is most of our digital fabrication processes are feed-forward. So that means there's no synchronization between the computational model and the physical environment. The second big reason is that there's a very inflexible distribution of tasks. That means either a human is making it or a robot is making it. But if we look at reality, things change. If we look at construction sites, parameters change. So we need to have a more flexible task distribution. And third, very importantly, we lack a lot of human interaction capabilities. So that means we lack tracking systems and user interfaces to inform and instruct humans about fabrication tasks, and include especially their decisions and intentions back into the computational framework. So actually give them more adaptability and more freedom to move within a computational network instead of limiting the freedom. And this is actually what we are researching now at Xaya Lab in architecture, to extend what we are used to, which is looking something like this: a human sitting behind glass walls cannot interact with a robot on time intuitively, to something like this, where we can say that humans and robots are sharing the workspace, which of course sounds nice, but brings a lot of complexities. Because suddenly you have a lot of moving actors and agents and a lot of intersections of workspaces. So we really see the need for that. And I want to show 4 projects that kind of tackle the individual things that I just mentioned, with intuitive interfaces, intuitive interactions, and potential computational models that we have, and user interfaces to allow humans to interact with a machine on the fly. So I will start with a project that does not include robots. I'm sorry about that, but this was actually the first one that I started to work on that showed me the importance on why we should not just only augment the human. Because originally everyone said, okay, but why do you need the robot? Maybe we went all the way the wrong direction. We don't need construction robotics. And it was a project that I started in 2018 actually, end of 2018. It was my PhD project on augmented bricklaying. And is up until now still the largest building built with augmented reality. I was using visual inertial object tracking algorithm in collaboration with Timothy Sandy and Katrin Dörfler. And in total, we built 14,000 individual bricks in Greece. And it actually gave me, even though there were no robots involved, it gave me a lot of knowledge on why and what we need to include a human in the computational logic. This was kind of the setup that we had. So we said, okay, a human is placing the bricks. We're using object tracking or visual inertial object tracking to detect bricks in space. We need a computational context-aware software that allows us to know where a brick is and where it should go. And I call it augmented reality. We did use screen-based augmented reality. I will also explain in a second why. Also here, construction is a little bit harder than lab research. We decided consciously against head-mounted displays because they did not work well for on-site construction. And it started with, so this was actually a building built by Gramazio Cola in, I think, 2012 or 10. So it was the first building built with robots. They laid all the bricks with robots. And we had a client coming in to ETH and say, they want exactly the same thing. And then I just started my PhD, and they asked me, isn't there something else we could do that is not a repetition of research? And I said, well, there are 3 ways you can place complex brick walls. The first one is pure manual fabrication, so you have physical templates and guiding systems. But it's very time-consuming, it's very expensive. Of course, we can place it with robots. But there are problems with robotic fabrication. For instance, there are limitations for on-site use, and you have problems when you use materials such as mortar. You have problems if you use materials such as handmade bricks. So third, we have augmented fabrication, which actually has the potential to combine human dexterity with the geometric precision of machines. And this is how I started. I said, okay, let's go for augmented fabrication. They put a trust in that, and they said, okay, you have 1 year to do research and 3 months to build the building. So I started to do the research on what is necessary, and to build with augmented fabrication, I needed to be able to inform humans on where and how to assemble complex brick walls. So for this, I tracked the position of bricks in space using visual inertial object tracking and combined it with current CAD models and a craft-specific user interface. Why is that necessary? Because, of course, we still work with architects. They have their own work environment, which for us is mostly Rhino and Grasshopper with Python and an open source library called Compass. And we needed a craft-specific user interface because we were working in Greece. I don't speak Greek. So I needed to find something that allows bricklayers to intuitively understand what they have to do for a task that sounds banal, but it's actually quite difficult, how to rotate an object 3-dimensionally to reach a specific position. And also because it was an actual building project, I was researching on how to do it physically in space. What's the hardware setup that we need? How can we actually produce something like this? So the whole system was made portable and combined with a screen-based augmented reality system. And this is what we shipped to Greece with some knowledge in me. And one of the hardest parts was, however, to develop this craft-specific user interface. So that means informing masons on how to assemble brick walls intuitively. And I worked closely with masons, and I laid all the other bricks where you see the fingerprints on it. And then the bricklayer came in and didn't leave a single fingerprint. And then I realized it's because they are tapping the bricks with their dowels. And then I started to understand how they see 3-dimensional rotation is not how we do it when we are used to work in 3D software. They see it in 2D movements to reach a specific position. And then I started to understand that this is what I had to include into the user interface for them to start to understand what they already know in a faster way. So I just translated the position of where the brick is currently to where the brick should go, and they saw specific arrows with a length. The length and the position of the arrow showed the bricklayers where to hit the brick and with what strength. Once they hit it correctly, the arrow disappears. Also, I showed them the mortar amount, just as symbols, because I cannot tell them something precise. They start to measure, it takes too much time. So I just showed them how much they have to fill their tool to actually reach the amount of mortar on the left and the right side. So here you can see an example where it was detecting the current position of the brick, and on the right side you can see the arrows that inform the bricklayer where to hit it. You see that we were using an edge detection algorithm. Back then, we still had it separated in 2 distinct interfaces. At the end, we overlapped it. Here you can also see how much mortar they actually could remove, so that the algorithm actually worked quite well to see even some noise, and the real-time update of the errors on the left side. And we translated that to what they saw on site. We overlapped it, so we didn't have two interfaces anymore. We just showed them one interface that included everything. And that's how the bricklayers worked. We had it split in two people. The reason for that was that we were tracking everything with an IMU and a camera system. And we were trying to place it on the human, but because hands are always in front of the camera, we actually were splitting it in two people. So one person was just responsible for tracking the objects, and the other person was responsible in adjusting the bricks. And here you can see the design that I was creating for augmented bricklaying. It was the entire facade of these 14,000 bricks. And the whole idea was that it's something that you could not see with your just by eye. So you only see it after you finish an entire wall. So the wall elements were 5 meters by 5 meters. I'm sorry, I don't know. I only know the meters. And this was the setup that we had on site: screen, the scaffold, the shading system, and the scissor lift. And some pictures here on how the walls actually looked like at the end, and how the bricklayers were placing it. Here you can see actually my PhD student now, she was already part of that project, placing the bricks with the masons. Part of the user interface and the final brick. Of course, not this one, as you can see, but this one was the part that we were developing. You can see some video snippets from the construction site itself. So in the end, we split it in multiple teams that were wearing two different setups, two separate setups. And once the bricklayers actually started to be using the system more often, they could use it alone. So only in the beginning, they had to be like multiple people. So we managed to finish everything in 3 months under outdoor conditions in Greece. So we had summer, bright sunlight, and managed to finish everything on time. And here you can see some pictures of the elements. Of course, what was very interesting for me as I was doing my PhD on it was I could track the exact position when people started to switch to the next bricks. Because I was tracking, you saw that we were using game pads back then, when they actually approved the brick and went further. I did not limit the freedom of the masons to decide when something is precise enough. Why? Because if they start to become too picky, and I say picky, the errors disappeared with an accuracy of 5 millimeters. I tested it, anything under 5 millimeters led to people taking an hour or more. And here you can see the learning curve that bricklayers had. In the beginning, I tested these parameters. I was like, okay, what if we try to be 2 millimeters precise? And because we have this imprecision of architecture and construction, you cannot be too precise. You need to find the sweet spot of precision and time. And here you can see in the end, we actually managed that each brick was around 3 minutes, which is approximately the same time as for a straight fair-faced facade a bricklayer would take. And here are some examples on that. And why I always like to show this project first is it showed me that there are two things I need to include in a digital model. First, I need to include human intentions. That means I need to understand what the human wants to do. Second, I need to include where objects are or where humans are in the control logic. And third, I don't like to lay bricks. I had to lay up a lot of bricks for this research project, and I realized I don't want to do that. And I don't think humans want to do 14,000 bricks. But I also realized what I want to do. I want to lay the one brick that makes a decision. I want to place something that actually changes something in the design or corrects something. So I want to give the input and not do the entire physical labor. So then I said, okay, so it just shows me that we need this human element in hybrid construction. And I went on to a next project, which is called interactive robotic plastering, which combined an augmented interactive design and fabrication system with a robotic plastering process. And also here, it was a construction period of 3 weeks, where we designed and fabricated on-site without a predefined model. And it was the first time that actually we had a combination of plastering process compared with an interactive fabrication setup. So here you can see I switched to say, okay, what if the human doesn't produce at all anymore? You only have the machine. We have a projector for the augmented reality interface. And not just do we have a computational model, but it's also interactive. So that means there is no 3D model before we start fabricating. If any one of you ever did some 3D printing, you know that you have to finish your designs before you start to send it to the machine, which is great if everything works out. Once you have a problem, it costs you a lot of time. So what do we have to do to actually create digital models that allow you to change them on the fly during fabrication? So for that, I combined 3 parts: an interactive design setup, an augmented reality system, and a robotic plastering setup. And for IROP, that's the short name for that project, we used a controller-based interaction system to enable humans to interactively design and fabricate articulated plasterwork in situ, where we took, for instance, the building structure and the as-built state of the ongoing fabrication into consideration for the next phase. It also allowed humans to create complex digital models in minutes and rapidly generate multiple design alternatives. It also allows humans, and that's very important, with limited programming skills to instruct a robot by demonstration. So the system architecture of IROP consisted of a computational setup allowing users to choose a style, and I will explain in a second what I mean with that. A user interaction tracking setup with projection mapping for the interactive design mode, and a robotic fabrication setup for plaster spraying. So the software of IROP had 3 different key modes. So the first one was humans could define an aesthetic style of the plasterworks. So what do I mean with that? If architects design a building, we design it, it's done, we send it to the construction companies. And I was like, well, isn't there maybe a more modern way, a more interesting, more interactive way how we can design? And I thought about the idea of style and Photoshop, where you use brushes to actually change the style of a line that you give. So the idea was to concept similar to Photoshop brushes, that users can use different styles but translate them into 3D space. So these styles allow humans to translate and remap analog inputs, such as hand movements, into robotic output. And the purpose of the style system is to allow creativity while still ensuring that whatever the human is designing interactively still complies with material and machine constraints. So if a craftsperson is going on site, they cannot break the robot, they cannot break when they work with plaster, and they can directly produce something that they like. An example of such a style system is, for instance, the carving effect that you can see here. And it just translated the distance of your hand towards the wall that you wanted to spray on to a different carving or smooth effect. And the reason for that was because we were spraying with air. It was still distributing the liquid plaster. So the closer you had the nozzle to the surface that you were spraying, the more you had this kind of ripple effects. And this was just one example of what you could do with kind of this translation of human input to robotic output. The second mode of the software was the interactive design mode. So that means the system provided an audiovisual guidance system to instruct humans while they were designing on site. Here you can see a photo of one of my students using the system. And one of the reasons why this was so important, way more important than we thought, was because purely visual cues are not really working well on construction sites. So we had to inform humans in the form of voice cues and tones of major events.
Welcome to the construction
such as the start
site.
of the system,
Please mark the points on the ground.
localization,
Points are marked. Projection is starting. You can
and
start
when
drawing.
they started to draw. And to test if something like this would be feasible, I tested 2 user groups, so designers and plasterers, to use the system. So the designers were my students at the ETH Zurich, who joined the research for a period of 2 months. And they were designing with my software framework their own styles within the computational framework, from very abstract interpretations, so an agent-based filter system, to a hand-drawing filter system, which is a one-to-one translation of human motions into robotic motions. They actually picked the middle one, which is in between, to design and fabricate a full-scale architectural prototype over a period of 3 weeks on an abandoned construction site, using the robotic plaster spraying and the interactive design. And here you can see some of the pictures of the results to show that you could use such a system to design and fabricate novel forms of three-dimensional plasterwork on site. So there was no 3D model beforehand. Everything was designed on site in 3 weeks and produced in 3 weeks. And then also the user study with plasterers showed that iRob was a system that they can imagine to combine robotic plastering with their own crafts knowledge. But then again, I said, no, but now I cannot produce anything by my hand. So maybe I want to be included a little bit more. So I thought, okay, while augmented bricklaying shows the human being fully instructed by a machine and fabricating, iRob shows a machine being fully instructed by a human fabricating. So what about the middle ground? What about the combination of both? And there came Tie a Knot, which examined the combination of manual and machine assembly for complex wooden structures using rope joints. So very similar to the first project that I showed, augmented bricklaying, this study included manual human assembly actions into the digital twin, but it extended it with an open-ended design process, so an idea coming from the second project to investigate what does the combination of both make. So here we have both humans and machines fabricate together. I used phones for an augmented reality interface. I kept the idea of a computational model that is context-aware and interactive. And I used, similar as augmented bricklaying, a visual inertial object tracking system and manual probing with the robot, so using the robot as a measurement device for tracking objects in space. So here we investigated how to build complex structures cooperatively. So manually placed elements should not disrupt the digital workflow, but should be integrated in a digital twin and should be able to result in follow-up robotic actions. So that means a cooperative assembly workflow that consists of turn-taking tasks between 2 humans and 2 robots. And the humans could initiate design and assembly cycles that were then continued, assisted, and completed by the cooperating robots. So this means that specific tasks are distributed to humans and others are clearly distributed to the robot. And we tried hard to find the perfect architectural example of why one task should be distributed to a human while one task should be distributed to a robot. And we found something that we call these white triplets. So white triplets are made of 3 struts. So one from a previous element here in gray, one placed by a machine here in blue, and one placed by a human. The human one in yellow was distributed because it's actually the hardest one to put in. The blue one can be just placed under or above a previous stick, so it's easy to place with a robot. And the yellow one is actually the one is more flexible. Sometimes structures move. So this is the one that needs adaptive interaction. And the whole structure was made of these white triplets that define the structural logic of the system, which is a reciprocal space frame. So to stabilize the structure and connect the struts, I chose a manual rope joint connection to also ask the question, how can we combine manual joints with precise robotic fabrication? So also this part examined the architectural potentials of cooperative assembly. So everything that is in this project is difficult if you work with robots. So the human is pulling, the human is moving structures, is applying force. And how can we build a computational model that allows both? So now I want to quickly guide you through the cooperative assembly logic. So we have 5 important steps. So the first one is, again, an interactive design. That means humans could decide in which direction a structure should grow throughout fabrication. So let's say a craftsperson realizes they cannot reach the wall. They can adjust this in small or big portions. That means humans can decide which direction the structure is growing. For that, they had to pick which Y triplet is the starting point for the next one. After choosing the starting element for the next Y triplet, the second strut was placed by the robot, as you can see here. And the third one was placed manually. And due to the nature of reciprocal space frames, this element is the hardest to fit in, as I explained before. And therefore, we placed this to humans. After the 3 were placed, the human connected all struts with rope joints. And because the last one was placed by hand, it was not precise enough. So that means we had to actually read in the position of that stick to allow the robot to have a follow-up placement of the next stick on this specific stick. So we tested 2 different tracking methods to register these manually placed elements. The first one was, again, a visual inertial object tracking, and the second option was via the robot, where we probed 4 reference points on the strut to define position and rotation of the strut. So also trying to understand if a robot can be more as a placing instrument, but also as a high precision measurement instrument, seen more like kind of moving away from the idea of a robot on construction sites purely as these big industrial robots used in car industry, more to a hands-on tool that the craftsperson could really move and use throughout multiple steps of the fabrication. So here you can see how we built the proof of concept timber structure. You already see that a lot of the research that we're doing always involves the building of structures to actually evaluate if something like this is working. And also here you can see some images of like the wooden struts that we placed. And you see the color is pretty one-sided. So we placed 38 wooden struts, 20 of them manually and 9 only with the robot. So actually this showed us that first we were like, oh, that's a really bad sign. But then I started to understand that the ones that are placed that are difficult to place towards the ground and towards the wall are placed by the human. And the ones in the center, where a robot needs to hold it to give me global accuracy, to give me anchor points, were actually placed by the robot. Here you can also see some images of discrepancies between the different tracking methods and the visualization of the translation deviations and the rotational deviations. And this project actually showed that it has a lot of potential. It also showed the downsides of the things. An example for that was we extended this project with cooperative augmented assembly, actually the master thesis of Joe and Eleni here in the audience, where the whole task was, let's take out some things that made it too complex and investigate other things that could be maybe pointing the right direction. So in comparison to what I just showed you before, this project still used the robots to hold elements in space, stabilize the structure, what I realized was really important in the previous one. We extended it to mobile robots because I realized that this is something that is very important, especially if we talk about on-site construction. And started to work more on task distribution. That means clear flexibility on what is placed by a human and what is placed by a robot. Also here we included structural stability and robot reachability maps into the design generation. That means tasks that were distributed to the robot, we actually already included what is reachable by the robot at which position. Because what we lacked in the previous one was why we only placed 9 struts was it took a lot of time to place things with a mobile robot or generally a robot. So any move like collision detection, placement of objects in space, and even now with mobile robots, it takes way longer than a human placing something. But we still discovered that it is important to keep the robot, because if we take the robot out of the calculation, we are not able to stay precise. So we use the robot in every 10th element, approximately, to keep an approximate accurate positioning. Which sounds like a contradiction, but actually it's exactly what we need in construction. Something that allows you to stay approximately nearby where you should go, and not a deviation, an accumulation of deviation that becomes 10 meters after you build a 10-meter structure. That's always the problem with construction robotics, your large scales. And another thing we started to to investigate is what kind of interfaces do I need? I mean, in this case, we had mobile robots, so we needed to know where to place a mobile robot approximately, and to also allow humans to instruct a robot. So now we started to develop an interface that allowed humans to see what a robot is doing, predicting the movements, but also telling a human on what to place manually and the options that they have. So more direct interaction between, do I want to distribute a task to a robot or to a human? And here you can see some examples of the structure that we were doing there with the two mobile robots, a phone-based augmented reality app. So this time phone-based because most construction workers have a phone. Most construction workers use a phone. And even though head-mounted displays are great, they are not really used, especially not for on-site. So here you can see some of the examples of what the user could see, how the user could predict the tool path of the robot of placing a specific element. So starting to work on kind of issues such as safety, informing humans on specific positioning and reachability of the robots. And task distribution. We extended it to a third case study, which is augmented timber assembly at Robots in Architecture conference in Toronto this year, where we built another structure, investigating especially more the idea of data structure that we need. Because the more and more I work with robots and humans, the more and more we see the lack of great data structures and computational networks that allow you to describe a structure. So usually in architecture, we only describe geometric attributes of a structure, but to actually facilitate a shared digital physical workspace between humans and robots, we also need a shared and adaptive data structure to store more than purely geometric descriptions. So currently we are using Compass, which is an open source library, and I'll show in a second our contribution to it, and an assembly information model for design and robotic fabrication. So we link geometric information with additional attributes via an edge graph data structure, illustrating the connections of elements described through nodes and edges. So in this framework, individual elements are represented as nodes and edges, and they capture the relationship between them. So information about the elements is stored in nodes themselves, while information about the relationship is stored in the edges. And why is that important? Because we do a lot of assembly. So that means I need to inform humans the dependency and relationship of one element in the structure to another one. So I need to say which one actually builds upon each other. And I need to actually describe also additional things such as what kind of geometry is it? Is it placed by a human? Is it placed by a robot? And allow people to override these things. So once we have the data structure that contains all this semantic data for assembly, the whole next question is the sequencing. And the sequencing is, of course, a project-specific task, but the data structure, such as the graph data structure, helps to organize this information. So sequences can be simple linear traversals over a graph, something like this, or they can be very elaborate. So we wanted to keep it open so people can actually create very complex dependency graphs. And also, we worked a lot more on how we can use mobile robots. So for this, we utilized marker tracking. So every time a robot was moved, we get a snapshot of the robot frame in a marker frame that is fixed in space. And by that, localize the robot within the world coordinate frame. And it was very important that we switched. Before, we had two separate coordinate systems, the localization of the phone-based AR and the robots. And now we switched to one, because we realized that it's this convergence of the two individual workspaces that is very important for the human to understand where the robot is localized and vice versa. So each time, again, we move the robot, we track the markers in space, the same markers that we actually used to localize also our digital model of the phone-based augmented reality. Here you can just see some pictures and some videos of how we placed the individual sticks but you also saw that also before. And some of the snapshots of what the user was seeing. So here, for instance, we also we worked a lot on the idea on how multiple users can access the same app. So let's say you have 4 or 5 people work on a structure. How can they send robotic commands without endangering each other? So we actually worked a lot on a system that asks for rejection or approval of robotic actions throughout multiple devices. Because of course, the more you become multiple devices, the more difficult it becomes to actually inform everyone in that workspace that a robot is about to move. And a lot of the research went also into that direction, while still allowing humans to place something difficult, like, for instance, the joint connections, using the robot for what they're good at, as placing objects, stabilizing it, to build a structure that is only possible together. I want to end the talk with something that I'm very happy that we managed to release this summer. Another work that one of my PhD, actually both of them worked on it, and Joe was heavily involved in the writing of the code. So all the projects that I showed led to Compass XR. What is Compass XR? Compass XR is, in architecture, the first open source framework that tries to combine all of the ideas that I just told you in an open source way. So to streamline extended reality workflows, to ease the implementation of human-machine collaborative applications and architectural research and educational environments. And it's more than one framework. It's a little bit more complex. So what we developed is 3 main key things. It's a Python library working in Grasshopper and Rhino to allow you to communicate with cloud services, over cloud services with AR applications. So we developed diverse AR applications that can read in different assembly sequences. So for that, we use different kind of communication protocols, and we implemented them, such as Firebase, MQTT, and ROS. So this is a more detailed example of the communication architecture that we were using, where you can actually see what we use the different communication protocols for. The whole idea was to build a setup and a system that allows you to communicate with a lot of different phone clients, robots, and computers at the same time. So the idea of the distributed systems to provide users directly with a network to stream the design on phones, interact with robots on the fly, and instruct them. We also provide diverse different geometries that users can load. And with that diverse geometries, we also came with the whole idea of the computational logic that allows you to describe what I just said, it is edge graph data structure. Here you can see it as a simple example in a brick wall where each brick is a node in assembly, and their spatial relationship is described in their dependency between the edges. So based on that, we could generate an assembly model and a construction sequence plan. And this allows people to, for instance, describe construction sequences, as you can see here. So you need to lay the first row of bricks to lay the next one. But this is actually independent to the software. The software just allows you to describe this kind of hierarchy between the elements. And why is that important, for instance, in architecture? Because you can see a wall with timber elements has different priorities of building. So you need to place first the first one, the side walls, and the upper one to actually make the filler ones. It also says that these ones can be placed at the same time. So multiple users can place things in one structure in parallel. So you're not depending to one person anymore that is leading everything, but actually you have one system that allows multiple users to work in parallel without hierarchy. And also it allows people to preview a structure in AR with specific parameters. So for instance, which element should be built by a human, which element should be built by a robot, which one is already built, and which one can I build. And it was already used for 4 case studies. Some I showed you already. The biggest one just finished in Kaschlach at ETH Zurich, where they used it for a large timber construction to control robots and humans on site in the assembly. Of course, if you if you want to use it, that's where you can find it on GitHub. And also detailed documentation if you want more information on Compass XR. And that's where I end my talk. Thank you very much. I hope I was able to show you a little bit about construction robotics and the tendency where we're going to. And again, if you have any questions or if you want to contact, please write me or pass by the lab. We're always happy to show you our current research. Just installing a motion tracking system and an upside-down hanging robot. So there's a lot of exciting things happening in the lab, working towards more of human-machine interaction. Thank you very much.
Wonderful. Thank you so much, Daniela, for that fascinating talk. All right. Any questions? We have a few minutes. Any burning thoughts? All right, great. There you go. Speak to the microphone.
Okay. Thank you, Professor. So impressive presentation. I really like your research. And I only have one question. What do you think about how to ensure safety when your people interact with large-scale construction robots? So yeah, this question is more related to engineering questions. So yeah, thanks so much.
Thanks for your question. We are laughing because it's actually a research that we're just starting with one of our PhDs. There are a lot of things you have to tackle when you want to ensure safety with large construction robots. As you saw, we work with ABB robots. So once we become large scale, they are not collaborative anymore. So there we have to start to become really careful. And I think we have to be careful in two directions. First, we need to inform humans in real time about dangerous zones. So you have different zones of interaction possibilities, right? So you have the safety zone, which is green, which is fine. And then you have the zone where you come in close proximity with the robot, but the robot cannot touch you yet. And then you have, of course, a zone where the robot should stop. So I think you have three different approaches where you say, okay, where it should stop, where it can actually hurt you, it should stop. But what is way more interesting is how do you handle computationally and logic-wise this kind of zone before the yellow zone, before you start to interact, or before you go into the red zone. So do you tell a human to leave? And how do you do that? Or do you make that the robot reacts in a different way? And I think especially in construction robotics, it depends. If you talk about additive manufacturing, you cannot just make the robot move away because it, for instance, extrudes concrete. The moment the robot moves away, you're actually destroying the structure you're building. So you have to think about more complex scenarios in this case. Also because I think the fifth slide or something like this shows you, in architecture, we are very often in the orange or like the yellow zone and the red zone because we're actually adjusting something on the end effector. So it cannot always just lead to complete shutdown of the robot. So there we are discussing to actually work a lot more on complex instructions to the robot, so either slowing down and instructions at the same time to the human of what does it mean that you're currently at that position. So how do you show a human in real time how to leave the dangerous zone without freezing them? And there is actually not that much research out there yet, purely because I think one reason is that we did not face that problem. Everyone thought that we will be fully automated soon. And the second reason is because it's very complex. And everyone thought collaborative robots will come, as for instance, Universal Robots produce collaborative robots that stop when they hit humans. But you never can go higher than 30 kilos payload, because if you can't, otherwise you're not going to be a collaborative robot. So I think we're approaching it two ways. One is the interfaces towards the human, the behavior towards the robot. So should the robot start to retract, give you distance, and for what construction scenarios would that make sense? For assembly, it would make sense. For additive manufacturing, it doesn't. So yeah, it's very interesting. I would say the first approach would be to actually evaluate it and test kind of the user interfaces as well as the reachability maps from the robots and humans, while they're both moving agents, yeah.
Awesome. Let's see.
Thank you, Professor, for your wonderful lecture. I have a question that what do you want to do in the next step? Like, for example, is it possible to introduce AI agents to construct as an organization and human as a manager to interact with this robots organization, with various ways, like the natural language and other things? Is it possible, or yeah? Thank you.
Thanks a lot. So we use machine learning for specific things. So of course we use it for sensor system evaluation. So let's say you have a sensor and you have to detect objects in space. So this is the most hands-on use that we have for machine learning and AI. We just started in a lab a more changing the way how we actually want to instruct robots. So not instruct robots by defining the position where a robot has to go to reach a final goal, but actually just describing the final goal a robot should reach, and figuring out through machine learning the necessary steps. A very interesting research area that we also started with a project called Robotic Territories now at Princeton is the idea of kind of evaluation of intentions of a human on the fly, so that you actually do not have to give instructions anymore, but through object detection or camera vision systems, the software can detect what you aim to do or what you try to do as a human, and the robot starts to try to assist. So there we have to completely change how we use our robotic planning systems currently. Because as you saw, most robotic planning systems that we have in architecture, you have a final position and you calculate from the current position of the robot to the final position all the necessary steps, you do the simulation, and then you have the placement. So just by saying that I think you're trying to stack things, let me help you stack, it's a completely changing the way how we actually have to program. So we use it more in this way. And I do find it very interesting. So I think this approach of rather describing a goal than the steps necessary to reach that goal is, in my opinion, the right way of using AI or machine learning in the robotic planning process. And of course, in the object detection, this is this is very common now, and this is necessary.
All right, and I think this will be the last question. Oh, second to last.
Hi, thank you so much for the talk. I think the part about this presentation that I thought was really interesting was that a lot of your robots are just out in the field. Like they're doing a lot of work just outside in these remote areas. And I think a lot of robotics is still very much in the lab. So I'm really curious about what is the preparation required to take these concepts, develop it in the lab, and then move it and prepare it in the field, especially because you're saying it's 3-month time scales, which seems really, really short to me. So I'm curious about that process.
It's actually, it's one of my favorite moments if we actually go on site. And mostly it's everything that worked, everything that you think could go wrong goes wrong. And then you have to find fast solutions. I mean, now, because the first project that I showed, so now I'm working in this domain 6-7 years. I start to understand you just have to already build up computational models that are so flexible that it allows the user on site to override. And I think this is one of the most important things, is to allow people to override procedures that you thought as perfect. There's no such thing as perfect out there. There's only one thing, which is adaptive structures. So, and to design adaptive structures is very complicated. So you need user interfaces, you need user interaction possibilities, you need data structures, etc. So once you start to have this setup, it's becoming a little bit easier. But I do have to say, like, it's absolutely necessary to do that step. Because we started this research 12 years ago on construction robotics, and we still don't see robots in construction. We only see them in prefabrication. And the reason for that is that I think we don't often enough do the hard tests on our robots to just see that we try to reach here, but we need to go the really slow steps. And that's why I always show that the small incremental changes that we do from one project to the next. We say, okay, now the localization of the mobile robots was not perfect, but we realize it cost us too much time how we did it. So let's speed up the process next time. And I think this is like splitting it into like small tasks for each execution. This helps a lot. And to actually put it in dirty environments, because just purely what it does to hardware, it's unbelievable. Like on the augmented bricklaying, all our computers burn through because of the heat increase in the backpacks. So simple problems like this also become very important in the overall thing, yeah.
All right, and now for you, the last question.
Thank you. Hi. So thank you for the wonderful talk and work, and that's a lot of hard work behind it, I realize. So I'm thinking about task specification for robots, and you've been talking about this. Obviously, it's very difficult. And however, that's a perfect opportunity with present machine learning AI techniques to learn from humans
Yes.
and execute eventually, and moreover, perfect that execution over time, because we may not need a perfect robotic execution, you know, from the first time, and maybe it's really hard to specify everything and take advantage digital twin and so on, all the information. So I was wondering, yeah, if there are tasks that you've thought or are thinking about where really learning from human, you know, I have a segment of 5-minute segment where the human executes, a human expert executes, and then I have the robot to do that, and eventually it will continue learning through, you know, executions from its own performance.
It's a very good question, because I'm like, with the plastering project, the original idea was plasterers could use it to actually structure, like instruct them, and then you can learn from it. And I realized the more we use the system, humans don't do repetition. I almost have the feeling it's not the physical action that robots need to learn, but actually the final goal. So the final okay of something. So it's rather tracking, for instance, hands, and then use that for machine learning. It's rather the understanding when is something good to go. So this is a little bit the feeling that I had. There was not a single construction scenario yet where I would say the repetition of manual movements was so similar between two different craftspeople that we could use that to actually repeat. I mean, there's one project by a colleague of mine which is on carving, where carving wood. But also there, it got nowhere because it became so complex with the material. So I almost have the feeling it goes more towards not tracking the physical actions, but the final intentions and prediction of intentions, and try to assist with that. Let's say you place a brick wall. Once I show with 1 or 2 bricks a good rotation, for instance, this is something that the robot could repeat until I say, for instance, it's going the wrong way. Then I need to instruct again. So I don't think we can produce something that is continuously, like you do 2 steps and then it will be automated entirely. But, like for instance, the next 20 steps, the next 50 are completely automated. I check in sometimes, adjust it a little bit. So I do think it goes a little bit more that direction. Or maybe someone finds another solution for that. But this is at least how I experienced it until now to work with it. Thank you.
Wonderful. Well, we have to wrap it up here, but let's thank Daniela one more time.
Thank you.